My name is Emil Jovanov. This month marks actually 10th anniversary from my first paper in the field of wireless body area networks for health monitoring. And it's been really amazing to see how much progress did we make in the last 10 years and how much closer we are to actual products. Like everything else, we also have exponential growth in this area. And just to remind us about overall system architecture, I'm going to use one block diagram from the paper from the middle of the road. That was only if we can get technology to work. Okay, good. This is just to remind us about overall system architecture. So what we are talking about is a cloud of sensors. Some of them are on our body, some of them are in our body, some of them are embedded in our environment. So all these sensors communicate between themselves, and they create synergy of information from individual sensors. In the meantime, we even have commercial products. For example, we have a pill that can be swallowed that measures core body temperature that communicates with other sensors in the network. We also have systems for deep brain stimulation that can also communicate. And all these sensors can, and systems can work much better if they have a big picture together. So for example, a drug pump can perform a much better function. For example, insulin pump can perform much better function if you know exactly what is the state of activity of user, if you know if the user is active or not. So all these sensors are communicating between themselves, and the natural place for integration of all this information is cell phone. Cell phone is your personal server that integrates this information. When you integrate that information, you can send it to the rest of internet that allows your physician, your family and friends, your social circle to access information relevant to your health. So in a way, this implements the concept of guardian angel that can extract much better information about your health and that can provide information about impeding conditions even before you experience any problems yourself. However, in order to make successful systems, we have to carefully examine design space. And we had several very good papers today that talk exactly about this, and that will be actually the topic of my talk as well. Why is this important? You can always pick up off-the-shelf sensors that can provide some functionality. You can attract some venture capital, create some early prototypes, and then create big disappointment for all this venture capital because they will realize that your sensor can work 4 days instead of 1 month. Okay, so it is extremely important, exactly what we were able to see today, to understand system design space. So I will just emphasize a couple of points. We are talking about heterogeneous sensors. If you have implanted a drug pump or your pacemaker, you cannot use Wi-Fi or Zigbee or any other standard. So we will have to deal with heterogeneous sensors, different communication standards. We will have to synchronize all this sensors together, and user identification and privacy is a very important issue. So hacking into your drug pump is a completely different issue than hacking into your home computer. Most of the systems are classical improvement of classical data acquisition systems. However, we have increasing number of sensors that perform real-time signal processing, and every real-time signal processing system will have critical signal processing latency. And I will give you one example today, because most of the other talks will be concentrated on optimization of power consumption. So what are the critical issues? The most critical issue, the issue that your physician wants to see is compliance. They want to see that you're using your sensors. However, that will be critically determined by size and weight of your sensors, and size and weight of your sensor will be determined by power consumption, communication protocol, and synchronization. I will give you today one example of our project that we are currently working on that demonstrates exactly importance of critical signal processing latency. We are currently working on a monitor that can detect and resolve freezing of gait of Parkinson patients. Freezing of gait of Parkinson patients is a very serious condition. It happens suddenly without any possibility to predict when it is going to happen. It can be triggered even with an optical pattern on the floor. feeling is that your feet are glued to the floor, so patients are trying to unglue themselves to continue walking. Very often they lose balance and they fall. It has been shown that if they have rhythmic stimulation, for example, sound, rhythmical sound, they will freeze much less often than if they don't have. However, since in assisted living facilities, they don't listen to hip hop very much, we decided to create a system that will be hip hop on demand. So general idea is to use inertial sensor to detect moment of freezing of gait and then generate a signal that will be sent to standard Bluetooth wireless headset that will deliver that kind of rhythmical stimulation, unfreeze the gait, and continue normal walking. So what we very often forget, and in published literature, they very often talk about detection of freezing of gait using 8-second windows. If you use 8-second window, that means that you are going to have 4-second latency. You don't have time for 4 seconds. So you will, in every system, you will have some critical latency that is maximum latency that you can allow in your system. In our case, this is approximately half a second to 1 second that still allows our system to resolve freezing of gait and continue normal walking for our system. So what kind of system design space do we have? Different microcontrollers will have different processing power and different power consumption. So the question is, how do we select a microcontroller that is the right microcontroller for our application? We had already one paper. I will just finish with one slide that simply shows that in our system, we are trying to go exactly in that high-performance DSP. However, we would like to also have longer battery life. So everybody is trying to reach this green Eldorado area and achieve optimal performance, satisfying maximum latency with as long battery life as possible. And our next presenter is going to talk exactly about that, how we can extend battery life of our systems.
Emil left the discussion on if you look at the design space, I'll look at one axis, which is the power consumption axis. And I've been asked to look at signal processing challenges, so I'll discuss a bit how signal processing strategies can help in reducing the power at the system level. To make the discussion a bit more concrete, I'll look at one particular case, and that will be the case of wearable cardiac monitors, so wearable ECG monitoring. We've discussed it already quite a lot today. The first slide will be just a review of a few wearable cardiac monitors introduced over the last few years. We've heard a great talk this morning by Professor Tumasu from TUMAS. The device is on the slide. I apologize if a particular device you're using or have developed is not on that particular slide. It's not an exhaustive list. It's just a summary of some of the prototypes or products that have been introduced the last few years. At IMEC, we've also developed some of these prototypes, in particular ECG necklace, which relies on IMEC technologies for the front end and for the algorithms. Our key contribution has been in decreasing the power and making these systems robust for use in ambulatory conditions. So these are all great devices. So it all looks very good. Maybe the problem is solved or maybe not. So there are some key issues that remain in terms of power consumption. And the main issue we have is that if I look at today's electronics, they're not sufficient to achieve the level of power consumption which will allow us to have 1 week, or as Emil just said, 1 month of autonomy. So here I show one case. That's the case of the ECG necklace. And you see two sub-cases. The first case on the left here, where the power is 8 milliwatt. That's a case where you have the full-blown functionality. So you want to record the data, you want to store the data locally, you also want to process the data in your microcontroller, and you also want to transmit the data wirelessly to a receiver, cell phone, or a PC. If you look at it, do I have a pointer here? No, probably not. So if you look at the power consumption, you see the MCU burns out most of the power. It's about 45% of the power. The radio and the data storage also burns out quite a lot of power. You see also on the right side of the slide, if you do some system-level power optimization, you can decrease the level of power consumption to about 2 milliwatts. So if you look at a lithium-ion battery, a small prismatic battery, 8 milliwatt will give you 2 days of autonomy. 2.2 milliwatt will give you a week of autonomy. So by doing system-level power optimization, you can get to 1 week autonomy. But this is not enough, again. We have to look at better or other strategies to reduce power. The take-home message of this presentation is that if you want to reduce power, we need to do three things. First thing, we need to look at alternative signal processing strategies. What can we do in analog? We heard great talks about that this morning. The second point is that we have to look at the global system design. It's not okay just to look at the DSP or the analog part. It's the overall system that matters eventually. And the third point is that eventually we also have to look at the circuitry and ultra-low power circuits, analog, digital, RF will also help in gaining or reducing power consumption. I have a couple of clear cases or clear examples in these following slides. The first one is analog assisted processing. We heard about what you could do in the analog domain. In this case, we can take the example of a beat detection algorithm. You have the option to run everything in the digital domain, or you also have the option to do some pre-processing in the analog domain. For example, you could extract the band power information in the analog domain and just leave for the digital part the thresholding part of the algorithm. What's the impact on the system level power consumption? Well, you can see on the slide that you reduce the power consumption of the system by a factor of 10, just by offering part of the signal processing to the analog domain. Another example is to do smart sampling. If you look at the ECG signal, not all part of the ECG contains the same information. So if we could do adaptive sampling, that means sampling at a higher frequencies in certain part of the signal, we can reduce the data rate and therefore reduce the power consumption of the radio. And this slides show that by doing such adaptive sampling, we can gain a factor of 6 in power consumption, again, at the system level. Eventually, we need to combine it all. So in this slide, it shows that if you combine both analog-assisted processing together with adaptive sampling, you can gain a factor of 7 overall in the power consumption. And then the last thing is how do we reduce that even more? Then you still have, on the right part of the slide, you still see that the DSP and the radio burn some power. So the possibility to reduce further power consumption goes through ultra-low powered circuit design. And this slide is a projection for some research which is happening in IMEC, in the areas of ultra-low power DSPs and ultra-low power radios. And we project that with the next generation radio, we'll be able to increase the power consumption, to increase the lifetime of a device from 5 to 7 days today to over 89 days today. And of course, then it comes down to your application scenario, whether you would like to have a patch that you will keep on for 90 days, probably not, but you can just look at it in terms of power consumption. A decrease in power consumption will be a decrease of the battery size and therefore a decrease of the size of the system, and that will therefore increase your compliance.
Medical grade network design issues. So we got a lot of smart people out here. Signal processing, not an issue. FDA, that's a problem. Now the FDA does a lot of good things, but the thing you have to remember is they have authority to regulate all clinically significant medical data, okay, including any component, part, or accessory. That means Welch-Allyn, who builds a medical monitor that runs on an Aruba or a Cisco or a Maru or a Trapeze wireless LAN. That wireless LAN, it's not regulated by the FDA now, but they have the purview to regulate that, okay? The FDA has a guidance document about how they're going to deal with coexistence of medical devices. And the reference is in the slide. But the point here is that we have that, and so we need to, as we take consumer concepts and we marry them into medical diagnostic space, we have to consider that the FDA does consider these as regulated medical devices. Okay, so this is my definition of a medical grade network, one that has been verified and validated to operate in the intended use. For example, real-time patient monitoring has a very different intended use than spot monitoring. So in real-time monitoring, that ECG is on me, and the clinician is depending on that device to tell him when my heart is in trouble. It's very different than the clinician coming in and measuring your blood pressure, and the clinician is there, right? So medical grade is abused. We have companies that sell a medical grade product. They are not medical device companies. And I want to introduce what just became an ISO standard, 80001-1, which introduces a risk-based solution. So our risk-based design methodology. It's nothing that we haven't heard before, but it's kind of new for hospitals. That when you get some new GWIS technology, don't just turn it on, test it, then turn it on. But to get into the point that Hari is very interested in is what are the network features? And then the next slide is what are the issues. So we really need a robust communications channel, right? Whether it's voice over IP being used for alarming, or we're taking home medical data, sending it over a cellular network for a clinician to analyze. If the data are corrupted or missing, it's worthless. So we got to solve the first mile and the last mile. In a hospital, we need a network that, for continuous monitoring, is very robust and deals with fast roaming. So when a client moves from one AP to another, or in the cellular domain, when they move from one cell tower to another, there's not an interruption in service. Or we need the software, the middleware, that solves that problem, that deals with packet latency and issues, kind of like the firefighter solution that we saw a little while ago. Strong bidirectional authentication and encryption. I'm over here looking at the Qualcomm demo, and one of the questions is, how does this solve HIPAA? Does anybody know what HIPAA is? Everybody? Right, basically it's a big act from Congress. They're always big, right? But a piece of it is protect and secure patient private health information. We need to monitor the performance. Just like you go in for a physical, and every time you go in, they measure your heart rate, your blood pressure, and your weight. They are trending these things. We don't want networks that suddenly die because they overloaded. We want to know beforehand so that the hospital, whoever's providing the infrastructure, can respond to the issue before they have to react to a fire. Redundant solutions, where if part of the network goes down, we still have a solution, and we've got to design for peaks, not averages, if we want to do real-time continuous monitoring and make it dependable. So problems to solve, actually, in all this body area network detection, there are a couple problems that came out. First of all, great, everybody in here has a body area network, and we're moving sensors around. How do I make sure that Hari's data is going into Hari's medical record? Especially when a clinician takes one sensor from one patient to another. That's a problem we've got to solve. Also, and as you move it from patient to patient, let's say we're using Bluetooth. Do you want the clinician to go through 6 steps on the cell phone to do the pairing every time they go in to change a patient? Well, they don't want to do that. So we've got to make these sensors be able to move quickly. Shared WLAN networks. Medical devices historically, if everybody's run on their own proprietary network. So when we go to Wi-Fi, everybody says, okay, fine, I'll run on a shared network, but I want my own ESSID. So GE has one, Philips has one, Draeger has one, Siemens has one, Agilent has one, Welch-Allyn has one. Well, pretty soon we run out of ESSIDs, right? So that's a problem to solve. How can we have all the medical devices sharing a network and allow the medical device manufacturers to be able to test to the solution? That's the reason we don't do it, is because I don't know what you're putting out there, but I can control what's on my SSID. How can we optimize power? 802.11a is an example, the ultra-wideband radio from Qualcomm. We have solutions where 802.11n is far more power efficient than A, which is more power efficient than 802.11b. And we need packet reliability. We saw for the SPO2 compressive sampling, that there are sampling and forward error correction solutions that can really help us. And we need to proactively determine when the SLAs are not met. So I just got my stop sign. So I'll turn the time over to Hari.
Okay, thank you, everyone. So Julien talked about low power. Steve talked about data integrity. So I would like to introduce some new signal processing tricks and remind you of some of the old ones that will come to bear here. There's one of the things missing here, pictures. The one that you see on the left-hand side, that's what Som presented. When you have a really power-hungry sensor, we can get fewer samples and still reconstruct the Nyquist equivalent. Essentially, we are doing things at sub-Nyquist sampling. We also did some work with Julien, Penders, and IMEC that's presented at the HealthCom, where we project the signals into a random space and then transmit the data. That's what I want to talk about here because that's more related to the ECG thing. So this is, I shamelessly borrowed it from Julien. The evolving radios, as he pointed out, it goes from, you can almost get 6-to-1 savings in the radio. For ECG, the data acquisition is really not an issue. We can do it like 10 to 20 microwatts with the right technology. So the question we are asking is, if I can send all the data to a receiver with better battery budgets, why would I want to do the DSP here? Then I can bring much better processing at the receiver. And especially for ECG, people currently use continuous 24/7 monitoring in ICUs, Holter monitors, emergency response. And in these situations, it's a wide ECG, and every patient generates 100,000 beats per day. There's not enough cardiologists to look at this and get any intelligence. So the commercial grade ECGs, like the ones from Welch-Allyn and GE and Philips, they use AMI EC57, and this has got published databases and annotations, beat annotations done by cardiologists. So we said, can we support the same functionality without the wires, untethered, and still be lower power? So we still maintain lower power, and now we want diagnostic grade quality. So the red line is where we put the signal processing path through the thing, and the black lane here, the reference annotations, and we get to see what's the sensitivity and what's the positive predictivity. And this is the kind of stuff that people report in EC57. If you look at the last 3 columns, those are the ventricular ectopic beats, the abnormal ones. The 4th column with compressed sensing, I start with 97% sensitivity, predictivity, and even at 35% packet loss, I drop only to 95.91. Whereas with Nyquist, I drop down to 35% predictivity. There's a loss of 60% degradation there. The other way to look at this is, oops, something wrong with the technology here. Now, there used to be a graph here that's not coming up, but anyway, I'll tell you what was in the graph. With respect to the, oh, there it is. Okay, I couldn't see it here. So the dotted line is what we are showing with the Nyquist. So my baseline is 0. I do not drop any performance. And as I introduce packet loss, how much degradation I get. The x-axis is the percentage packet loss rate on log scale, and y-axis is the degradation. You can see the solid lines almost at 0 till about 20-25% packet loss. And these are the kinds of losses we expect with the Nordic radio that IMEC had and the Zigbee radios. So that's really the key message. So we do see some sort of errors like this. So essentially what I'm trying to say is wireline replacement is a very tough problem, but we are getting there. Essentially improving the sensor life and signal integrity and making it in right form factors that people can use. But there's a bigger question. What is the actionable information that healthcare providers actually need? Is there a doctor in the house? I guess nobody. So essentially, we need to find out what is it the doctors actually use. Because if we just dump all this data, then it changes their workflow and they wouldn't know how to use it. So this is where some of the old signal processing things come in. Artifacts mitigation, pattern matching, machine learning, just like the automated Arithmeia software and the Utopia paper that you saw. So we can leverage all of these on receivers with much better battery budgets and solve this problem. So there's lots of interesting problems to solve with signal processing. Thank you very much. So,
okay, we'll have time for questions. Do you guys want to come? We have 3-4 minutes for the signal processing. Any questions, comments? Harry, do you think there are a lot of new challenges in signal processing, or are you taking old problems and twisting and massaging them?
Well, there are tons of problems. There is really no dearth of problems because we still need to make the sensors really small. And once you have a lot of sensors, they are all streaming the data. The latency stuff that Emil talked about, when you have two sensors that are not tethered to each other, and if you have a skew, like blood pressure estimation with SpO2 and ECG. So there's tons and tons of problems that we still have. This is tip of the iceberg. And all I'm saying is there's lots of established tools that we have developed for the last 50, 60 years. We can bring them all to bear if you do not have the restriction of having to do them all on the sensor board.
Perfect. Roosevelt?
So this question is for Julien. What is the programmability of the analog component? I understand that one of the reasons digital became so big was that it was scalable, it was easy to implement, and all that.
Yeah, well, it's a good point. It's very limited, of course. So that's why I mentioned what we call it here. It's analog-assisted processing. That means what you have to, when you look at your algorithm, you have your application, you define your algorithm. That took the case of a beat detection. You have a part of the algorithm which is very standard and very generic, and that will be used in many different applications or for many different instantiations of your same application. For this particular part, then you can definitely consider doing it in analog domain, providing it saves you some power. Some of the part will not, and I mentioned the example of thresholding, where the thresholds may differ if you have a lot of motion artifact, for example. So that's certainly something you don't want to move to the analog domain, but you need to keep at the digital domain. So it's a system design question, really.
The next session will be our challenges in computer science. I'll start with that. And then we have two other speakers that will talk about computer science challenges. What I want to mention here is that's a definition of wireless health. What I want to propose here is end-to-end research. I want to suggest what that means, give you some example of the kind of research that we do at UCLA in the Wireless Health Institute, and why do we call them end-to-end research, and why are they so important to be end-to-end. Okay, being a computer scientist, the first thing that we teach to students in our algorithm courses is partitioning. Assume you have numbers from 0 to 7 that you want to sort. If you partition, this is the first thing we start in computer science. First thing you can do is to partition this problem and then sort each sub-problem. And you see the result up there. You get 0, 2, 4, 6, 1, 3, 5, 7. That's not a sorted list, not even close to that. So if we try to solve wireless health problem, we get into the same thing. If we just divide the problem, engineers and computer scientists do their own piece, toss the data to the other side to doctors and physicians and nurses, this is what we'll come up with, something very suboptimal. And I'm saying this not because of sorting, but because of practice. We have another technique called pivoting, which results in quick sort, which we still do partitioning, but we do allow communication between subgroups, as you see below. Still the list is not sorted, but is much closer to a sorted list as it can be. And that's exactly what I want to emphasize in end-to-end research. Two aspects of it that I'll touch on today briefly is end-to-end research in computer science and engineering. Want to avoid the kind of question, my area of research is X, how can I apply X to solve this wireless health problem? I want to avoid that. The other thing is I have this gadget or this app, let me give it to a bunch of doctors or business folks and see how they can market it. Want to try to avoid that type of an approach also. So first about computer science. One of the first things we teach in computer science is models of computation. Whether it's a von Neumann machine or Turing machine, this is really the building block of computer science. And that's what I was referring to when I asked the question from Harry. For wireless health, we don't really have these models of computation. Complexity of a problem, whether a problem is hard or easy, whether a problem is NP complete or not, these are all based on models of computation, meaning Turing machine. I would like to encourage the community to come up with WH, or wireless health model of computation. What are the computing ingredients in these body sensor network, cell phone based, mobile, or what have you? There has been very little work done on that. For example, taking a full-blown RSA algorithm built for a very powerful PC and trying to put that in our shoes or EKG devices, that simply doesn't work because of computational limitation. We have done many examples of this. For example, we have taken the distributed model of computation, and in many things that is optimal there is absolutely non-optimal when it comes to many models of wireless health computation. And the result shows that you could really be off by the factor shown here, a square root of n divided by log n. For now, this is just a number and may not be meaningless. Point being, we need to go back to the basic constructs and start building on top of it, as opposed to starting very high level with our algorithms and techniques. I'm not going to go through details of these algorithms, but point taken is, cannot take a solution done for a different model, for a different environment, and massage it, or as we call it, hack it, to adapt it to wireless health. That is absolutely the wrong approach. Many of the folks who have experience with that here in this room would agree with me 100%. The other thing, I want to go and give you some examples of problems we have focused on at UCLA at Wireless Health Institute. I want to really emphasize that the only way to solve these problems properly is for doctors, computer scientists, engineers to sit around the table every week, not just once, every week, and it will take a year or two before they get the problem right. I'll give you some examples of that. These are some devices that we have built at UCLA, Smart Gain with Professor Kaiser, Activity Monitor, Smart Shoe, etc. And this is a quick web page, and the point about the wireless health and who the co-directors are. We have directors from public health, radiology, neuroscience, but more so, if you see the community involved, is medicine, nursing, public health. Without them, we cannot truly solve these problems. Let me give you some example. I think many of you have seen knee hammers, right? You all know what that is. They kind of hit, they look at your reaction. To us, that seems so unscientific. So about 10 years ago, we built a device which automates this. We put accelerometer, we measure the angle to make this repeatable every time. Instead of a doctor being angry one day, hit you harder, and hit you not as hard the other day, not so scientific. We built this, very proud of it. We showed it to our doctors and we said, are you willing to use that? They said, absolutely not. We showed it to our business folks and our tech transfer, and we said, can you market this? They said, you're crazy. We said, why? They say, your device will cost a few $100s. It will take 20 minutes to set up. The doctor doesn't have that time, and a $19 hammer will do exactly the same. So this was 10 years ago. From then on, we promised we will not do this in computer science labs all by ourselves. Now, there are a lot of rich set of problems here. Very interesting problem, resulted in a bunch of paper, but with all due respect to me and my group, absolutely useless. We learned. So the next project is WANDA, is weight and activity. It's a home monitoring system. From day one, every week we sat down with our colleagues in this particular, for example, nursing school. We did a 20-subject project. This is a remote monitoring based on an Android system for weight, blood pressure, etc. We learned from those 20 subjects. We did another 10 subjects for heart failure patient. That took another 6 months. We got all these results. We learned very basic things. I'll refer some of them to you in a minute. But these two and a few others really helped us to do a proof of concept. We learned many things in this project. Off-the-shelf projects is a good start, but is not enough. Remote updates are preferred by patient, etc. So this was a 3-year study. From all of that, we got all the results together, and we submitted a large grant, and it was funded last week. This is 1,000 subjects, used all of our studies, all of our learning. For those who are curious, large here means $10 million, not $300,000. So this is going to be fun. It uses everything we have learned, many research in computer science. Some of them I have highlighted. I'm not going to go through all these results. But many things learned about diagnosis, signal regression, adaptive early system, etc. So these are the things we learned that will be going on in the next project. These slides are going back and forth. Let me see where we are. Okay. So the next project is a drug abuse program. Again, we build a system from scratch from day one, every week, not once a month. Sitting down with our doctors in public health, design a system from scratch. This is the structure of the system. It has a QA system, activity monitor, etc. And we learned such simple things. For example, one barrier to success was one clinic felt that if they do urine drug test, that would affect the community and the patient perception and trust in the clinic. So they were not going to do that. You know, computer scientists, how would I know this without actually going to clinic? You know, what do I know about urines and people's perception and all that? So we really learned, and we adopted our technology to the things that we have learned in these systems. These are the electronic data collection. That was quite challenging. The databases, we were talking with Professor John Lodge about how to actually optimize and correlate these things. This is a really neat project. I have about 2 minutes, a minute. Gaming for health. This is mind-boggling. In US, average kids spend 44 hours in front of TV. So we came up with these gaming techniques where we connect the body to the video games to solve them. No time for that, so I'm just going to get to the conclusion. I'm just going through the slide. Don't count that against me, please. This is a very neat project about wound management. There is a huge demo there. This took about 2 years of working with nurses, with experts in the business world and operation. Go and see the demo and the clinical trial that was done for the past year and a half. Point, end-to-end research. Problems wasn't made up by me. Came up from the community, doctors and patients. I think that's very important. And I think John Stankovic will agree with that as he will follow my talk.
All right, so one of the previous speakers mentioned that we've come a long way in body sensor networks. And I agree with that, but I also think we have a very long way to go. And what I want to focus on are just 3 challenges, because there are too many to spend just 10 minutes on. And what the context is, I want to put wireless sensor networks on people, but also in the environment. And when I do that, I don't want the following to happen. I don't want my house to look like this, right? So we don't want wires. The systems will be heterogeneous, but I want everything to be wireless. And to put the context of the challenges that I'll bring up, basically it's a smart home, all right, where a person here might have a body sensor network on them. There may be sensors monitoring the quality of sleep, medication. But there's two things I want to emphasize. Number one, these environments are open, meaning the RF is going out through the walls and people can overhear. Secondly, it's uplinked either through the cell phone system, or the internet, so it's open. The second main point is that the systems are continuously evolving. Today, I'm not feeling well. My doctor gives me a body network to monitor my heart. Next month, I have a different problem. I have a different body network on it. People come to visit me. They have body networks on it. There is no system. It's continuously evolving, changing system, and that makes the problems really complex. Now, to go through the three challenges, I'd like to set the stage for each one with a hypothetical problem. So I envision in 2015, we might get a story from the New York Times that says, wireless sensor network kills patient, okay? And automatic insulin injector goes wild, kills patient. Or we might see something, wireless sensor network declares patient healthy, and it drops dead the next second. Now, the first one is more about an individual product, an individual device, to try to prove it's correct and it's safe, all right? The second one is a tremendously more complex problem. And so the first challenge is safety. Now, there's been a lot of hazard analysis for many systems, aircraft, process control, and many other applications. But I have not seen a good hazard analysis for systems of medical devices. And these new problems contain issues that are not addressed very well in the classical risk analysis safety systems. We have tremendous environmental uncertainties. We have non-expert users. In aircraft, we have expert pilots, we have expert mechanics. Here we have my grandmother, right? So we do not have expert users. We have the evolution of the system. It's continuously changing as a person's medical condition changes or as visitors come in. It's basically a system of systems that have to interoperate on the fly, and that connection and combination has to be safe. And on top of that, human beings are unique, and they don't have, we don't have Newton's mechanics to describe human beings. Right, so this is a tremendous, I think, problem and needs to be addressed. The second hypothetical problem is that I might see in the New York Times, unscrupulous insurance company drops coverage just in time for them. Okay, so they're monitoring you and they find out that you are getting sick, so they drop your coverage. And so what does this might look like? So here's some work we did. Let's say I have a house here, and it's a smart home to help you stay healthy. And we don't know how many rooms are in the house. We don't know what sensors are in the house. And the data can all be encrypted. Okay? And we put a device outside your window, and we listen. And we just hear the RF. And we can use an electronic fingerprint. All we need to do is detect uniqueness on a device. And so what we do is, say this person goes near this sensor, and it might be the refrigerator or the stove. What we can do is we hear that radio, and it could be encrypted. We just record it at what time it happened, and we say it's some device, we'll call it red, and we know nothing about it. Later, person goes somewhere else, we know it's a different sensor, that's all we know. And we just record it as a unique different sensor and what time. And then later, again, they move around, and we do this, and we collect the data, and we collect it for about a week. That's all we need. And then we run various inference algorithms. And what we can do is we can tell when you're sleeping, when you're home, when you're in the bathroom, how many kitchen visits, if you're showering or toileting or washing, if you're cooking, we can even tell if you're cooking hot food. And this then is all of the kind of behaviors and activities that get fed into subsequently deciding on disease. And so we can violate your privacy. Right? And HIPAA basically says you're not allowed to do that. So we need to start worrying about privacy on the wireless part and on the ability to just overhear. A third hypothetical problem is that suppose, you know, I have this sensor network in my parents' house for a couple of years, and all of a sudden we add a Wi-Fi router and maybe a new wireless pulse oximeter, and all of a sudden the system stops working. You know, how do we know, as the system is progressing over time, that it is actually still operating correctly? And what I'll call is that we need challenges, validation and revalidation of the system. And in a context of the systems evolving, and the systems of systems is a moving target. And I show a diagram of a burning building over here to just bring the problem out. I know it's not medical, but it illustrates the problem because we applied it to this. If we put a wireless sensor network in a building, and in that building, skyscraper, we have hundreds and hundreds of sensors, and we tell the fire chief, don't worry, if there's a fire, it's going to work. He says, prove it. So maybe you have ways of showing this initially. However, now, new companies come in, more Wi-Fi is in there, they knock down walls, they move walls, and the system isn't working. And the fire chief comes back every month, and he says, does it still work? And you have to show him if it's still working. So the process of validating or revalidating is a serious challenge. And we're calling it runtime assurance technology, where we need to be able to emulate sensor readings. So we can emulate a person having a heart attack and making sure that if we're emulating that the data's getting back right to the right people at the right time. And maybe we have to run that each couple of days so we know that the system's still running. We need to reduce tests to focus on key functionality. We're not worried about, in the fire example, we're not worried about an individual sensor, as long as the functionality is still there. And the same thing might be in a home. We don't necessarily need to know about every single sensor, but we need to know all the key critical functionality. In doing this, we need to overlap tests and system operation, because when we're validating, we still want the system operational, and we want to evolve the required tests because the system's evolving. And these are tremendous challenges, which I don't think we know how to handle it all yet. And just put this last slide up saying what the many other challenges, including, I'll call it physically aware data mining, more accurate machine learning. I find that, you know, when we say we detect things at 80% accuracy, 90% accuracy, that's not good enough. We're not there yet. Data association, many systems require, you know, people who wear RFID tags or have some kind of biometric to indicate who's doing which activity in the house, and that shouldn't be there. We should have it completely passive and be able to tell who is doing which activity and when more than one person's living there, and so on. So I will just stop there with those details not worked out.
Okay, so I would like to shift gears a bit and talk about what happens when we actually create these gigantic systems and we apply them to more than just a single house or more than a small group of individuals. So what happens when we actually create a system that's fairly ubiquitous, that involves larger scale populations? What kinds of problems appear? And let's see. There we go. So what are population area wireless healthcare networks? They're networks that combine environmental sensing with body area sensing and with a mobile infrastructure. The goal of such networks is more than just monitoring. It is also to actually provide feedback to individuals and to people on the backside, so to public health officials, hospitals, insurance companies, and so on. So it's a much richer set of problems that you're really trying to solve than just simple, does the person have a heartbeat or not, and is that heartbeat regular? So as I said, when you have such a complex goal, you really need to think about a whole set of problems that have to be solved. And what's really cool about these systems is that it allows us to start combining issues that have typically been studied by completely separate entities. So now we can start thinking about how to combine physiological factors, so things that would typically be analyzed in a lab when you go for yearly checkup, hopefully not more often than that. Interpersonal and psychosocial factors, so how do your friends and where you work affect your daily decisions and therefore affect your overall health status? And then ecological factors, so are you sitting in a car in high traffic every single day, or are you riding your bike to work, hopefully through a forest? right? So when you think about this, these different areas have been addressed by completely different specialties. And when you start creating a large-scale population area wireless healthcare network, now we can gather data from all of these areas of life, including things like what is your genetic footprint, and start understanding how genetics, how various things that you take into your body, along with all of the other factors, affect long-term health decisions. Now, looking forward, what are some of the benefits of being able to provide more sophisticated feedback to people? So we did a really cool study. In fact, it was led by Kevin Patrick, the head of preventative medicine department at UCSD, looking at if we did something relatively simple, if we monitor activity in patients and provide simple feedback to patients on a daily basis, multiple times a day, and if this feedback is designed in a way that's palatable, that people will tolerate and actually maybe even enjoy, will they change behavior? It was a very simple question. So we did this study over a period of 4 months, and the study focused on people who really struggled with obesity. So this is a population that typically doesn't like to move that much. And what we found is when you provide people with reasonable feedback, they actually do change their behavior. And the change in behavior is fairly significant. You can see that over a period of 4 months, we had significantly larger weight loss, which can be directly credited to increase in activity in the group that used our system versus the group that did not. What's really exciting to me personally is that over 95% of participants wanted to buy our system and would recommend it to friends and family. So it wasn't only successful in terms of showing that real-time feedback helps, but people also liked it. They valued what was going on. And this is something that really motivated us to think about, you know, how could we expand such a system to something far bigger than just simple activity monitoring? Now, one of the biggest problems that was cited with this study was energy efficiency. So think about when you start monitoring truly what you're doing physically 24 hours a day, 7 days a week. You know, this typically will involve accelerometers, a GPS, and you can think of a few other things that you would monitor. When you start doing that, you discover that batteries are really way too tiny. And that whatever we're doing really needs to be much more effective than it's been before. And in fact, this raises a question of, is there a way to optimize accuracy, energy, and performance trade-offs across the whole system? So for an example that I gave you, you actually do not need to gather all of the data and stream it to the backend server and then provide feedback to the patient. In fact, most of the analysis can happen right in site and can be, in fact, even learned. You can learn patient preferences. So what we did since then is we started studying what happens as we move these tasks. And these task graphs can be fairly complicated. The example I'm giving you is fairly simple. Can you actually get much higher energy efficiency? And the answer is that you can. You can get, we showed with preliminary results, about 80% energy savings if you do dynamic task allocation. So if you can decide on the fly, when does it make sense to do what in the system? An example would be if I don't have wireless connectivity, it does not make sense for me to try to communicate. I really should do my processing locally. And I should provide the best quality feedback I can. In fact, if you think about wireless health, you should not be relying on existence of wireless connectivity always, because there are a lot of conditions for which you need the feedback here and now, even if the cell phone doesn't happen to work. So this really motivated us to start thinking about how do we build a bigger system. An example of such a bigger system is the Citizens project that's been funded by NSF about a year and a half ago. In order to solve a larger problem, we postulated a question of what if we did activity monitoring together with environmental monitoring, with the goal of understanding how diseases such as asthma develop over time. So to do this, we pulled a team together with the doctor right there on the top of the list, Kevin Patrick, and people who actually address very different areas. So Bill Griswold looks at user interface design and HCI factors, because those are critical in people actually accepting the system development. Ingolf Kruger is a large-scale software architecture expert. So John just got done telling you that when you design these large systems, you're going to have fairly big complexity, and you'll have systems that need to be continually changing. So what is the software backbone that's going to allow you to actually make the changes at runtime and to monitor what is going on? My team is more focused on energy efficiency. Again, if you have all of these sensors, some of them which are stationary and perhaps use energy harvesting, others which are mobile, what is the right way to manage energy? Sanjay Dasgupta is in machine learning. when we have lots of different sensors and lots of different potential applications, you need to be able to design a set of algorithms that can leverage both the preferences of the user that's using it and also the context around this user. Perhaps there are things you can learn from various other people in your area, from the environment, and from other types of sensors. To do something like that, you need more sophisticated algorithms than just simple averages and to provide feedback. And then obviously security and privacy. So Horav is our security expert, and as you heard from John, security and privacy are really big challenging issues. So here's an example of what I mean by this large software infrastructure. What we have here is on the left side, you see sensor and actuator platforms. These platforms may exist in the environment, so they may be stationary, they may be mobile in the environment, so you can think about your cars and the buses and various transportation systems. You can have them on your body. You need to be able to validate these sensors. You need to be able to ensure that even if some of them fail, that you can still deliver reasonable result to the user, and you need to be able to upgrade them and include new ones in your system. Secondly, you have people who actually use the data. The people who use the data might be private citizens, like in our patient study, may also be public health officials, insurance companies, government, and others. The type of view into the system that you provide will depend on who needs the view and what kinds of privacy settings you have. So you need a software infrastructure that can actually scale this appropriately and manage it at a large scale. So some of the key realities that we need to face are that sensors will be very much commodity in nature. So they're gonna have to handle unreliable, noisy, and poorly calibrated situations. So in fact, calibration turns out is a huge problem. When you actually try to implement a system to be used by real life people, you discover very quickly that online calibration is one of the big issues to resolve. Failure is something you can count on. So how do you live with failure? And how do you design around failure? How can you So depending on what perspective you have, whether you're a government official, whether you're an insurance agent, whether you're a doctor or an individual, there will be different levels of data access, and there will be different capabilities. So you need a system that can handle these differences. So one of the ways to deal with this is to develop a reliable and adaptable hardware and software architecture. So you really, as Majid mentioned, you need to think end to end, from beginning to end. And here's an example of some of the things you may want to think about. You may have in your architecture various types of messages that you're going to be routing from sensors and from actuators to various individuals. You would also have perhaps different applications. So I have an example here on the bottom by number 5, cancer inference engine. Maybe there are some things you're monitoring that actually are known to cause cancer. So you want to know how often is this person doing or engaging in such activities. The other example is asthma inference. So you can think about people developing multiple different application level engines. In addition to that, there are some concerns that actually span across all of the differences. And that's shown on the top. So for example, power management, you're going to care about power whether you're looking at asthma, at heartbeat, or at anything else. So you need to be able to actually deliver the cross concerns in an adaptive manner. In addition to that, you need to enable people on the outside to improve on, for example, power management engine, depending on what the current needs are in the system. So to summarize, some of the key needs for population area wireless healthcare networks are advances in open software abstractions. So we really need to be able to deliver easy and secure extensibility while supporting all of these complexities and hierarchies across all different software layers. And we also need to think about how do we advance science and engineering of very large-scale sensor networks. So how do we extend machine learning techniques? How do we perform good reasoning about power issues? And how do we address security and scalability at the large scale? Thank you very much.